Hello, this is Mr. McMahon. I'm here to give you guys the breakdown on these notes here. I'm sorry I can't be there, but we're going to talk about exponential functions today. So this is just another family of functions that you guys have to be aware of. Exponential functions are usually written. I'll go ahead and write in this blank over here. They have some base. Right, this would be called our base. That's going to be an actual number. Usually we like to keep them small, maybe like 2, 3, 4, 5. And x is the input for this function. So this function, you put it in x, and it raises your base to some power. And we should know how to calculate numbers that are raised to powers by now. So a here, in this case, is going to be greater than 1 in most cases. Oh, sorry, my bad. It's going to be greater than 0, but it cannot be equal to 1. So, for instance, we could have fractions in terms of our base. Our base could be like 1/2. It could also be bigger than 1, like 3, 4, 5. It could be 100 if you really want it. But we can't let our base be 1, and that's because if we have 1 to the power x, well, no matter what number we put in for x, the output will always be 1. So that's why we have this restriction right here. So let's go ahead and just sort of plot one really easy example. We're going to look at this 2 to the x. Right, so I'm going to use the numbers -2, -1, 0, 1, and 2, just for simplicity's sake. And we can evaluate these things. Right, f of -2 is going to be 2 to the -2. Well, if you have a negative power, right, this is going to turn into 1 over 2 to the power 2, which is 1 over 4. Right, so our output here is 1 over 4, which means the point on our graph is going to be right around here. Okay, next one. F of -1 is 2 to the -1. Well, that turns into 1/2. So our output here is just 1/2. Excellent. At 0, when I plug in 0, this is a very special rule. So if we have 2 to the power 0, that's actually going to be equal to 1. In fact, any number to the power of 0 is always going to equal 1. So what you guys are going to find is no matter what base we have, the exponential function should always go through the point 0, 1, no matter what. That's sort of like a fixed point. And then f of 1 is going to be 2 to the 1, which is 2. So we have a 2 here, and we plot the point 1, 2. And then f of 2 is going to be 2 squared, which is going to be 4. So 2, 4 here. And so our graph is going to look something like this. Let's see if I can make a good sketch here. It's going to curve, go through that 0, 1 point, and it's just going to start exploding upward. Yeah, so that's a decent graph. You can kind of see on the left-hand side, it sort of has something kind of like a horizontal asymptote. So it's going to get very, very close to 0 as we move to the left-hand side of the graph, and as we move to the right, it's going to shoot off to infinity, positive infinity. So it's got very different end behavior from like polynomials that we've seen. Usually polynomials have only infinities for those end behaviors, both sides. This one only has infinity for the right side and an actual number for the left. So you've probably evaluated these for integer and rational values of x, but what about irrational exponents? How do we actually think about those? Because if you think about it, right, usually if I had something like 2 to the power 4, right, you can actually evaluate that as 4 2's all multiplied together. And even if you have rational exponents, if you had 2 to the power of 3 over 2, right, well, that's going to be the square root. Actually, I don't have to write that 2 there. Let me get rid of that. It's going to be the square root of 2 times 2 times 2. So there's still a sense where you can kind of evaluate this stuff even if you have fractions in your powers. Now, for the square root, your calculator will have to finish that calculation. But like over here, 2 to the power 4, we could actually do this ourselves. Right? That'd be 16. I don't know what this one would be equal to, but again, that would be more like a calculator question. But if we had an irrational number in the exponent, how do we actually think about that? So like easy example would be square root of 2. That's a very simple irrational number. It's a decimal point that goes on forever. So how do we think about this? Well, consider the following list, right? This list here. So I have a to various powers. Notice how, because these are all finite decimal numbers, these are all rational numbers. And so there is a sense to where you could essentially treat this first one in the list as a to the 14 over 10. Right? And if you can treat it that way, you can think of how you would expand it according to roots and powers. Right? This would be the 10th root of a to the 14. Right, that's something your calculator can actually spit out for you. And so because you can make this list in terms of rational powers, this list, as the powers get more and more complicated, the powers are getting closer and closer to the actual square root of 2. So what we say is the outputs in this list approach a to the power of the square root of 2. And so that's how your calculators are actually doing these things. They don't actually plug in the square root of 2. They plug in a rational number very close to it. But they do a number so close that you don't even notice the difference if you're calculating. So that's just one thing to think about. We also need to think about what the graphs of these in general start to look like. So if we were to graph 3 to the x, right? So at 0, we're going to go through that 0, 1 point. Right? At 1, we'll go through 1, 3. Right? 3 to the power 1 is 3. 3 to the power 2 is 9, so that's going to be around here. 3 to the power 3 is going to be 27, so that's way up here. Right? Somewhere way up there. And then these points over here will get smaller and smaller and smaller. Right? So we'll get that nice sort of exponential function shape here. Right, so this is kind of what 3 to the power x might look like. If we were to compare this to 5 to the x, it's going to look a little different. Right, so it's still going to go through this point, the 0, 1 point. But if we do 5 to the power 1, we're going to get this point over here. And 5 to the power 2 is going to jump all the way up to 25. And over on the left side, we're going to get values that are even smaller than what we got for 3 to the x. Right, so the graph is going to look slightly different. It's just going to grow much, much faster. Right, so I'm sure you guys have seen stuff like this before. So exponential growth, you have values or outputs that are growing very fast as you're moving to the right. Exponential decay is sort of the opposite. Right? And if you think about it, right, these negatives over here, it essentially creates a reflection over your y-axis. And so they should be kind of symmetrical, right? 2 to the x and 2 to the negative x. So if we think about the outputs though, right, 2 to the negative 1, right, that's going to be 1/2, right? So I plugged in a 1, I got 1/2, it's going to be way down here. If I plug in -1, right, I'm going to get 2 to the negative, put these parentheses here, -1, right? -1 is my input here. Well, -1 turns into +1, and I get 2, right? So at -1, my output is 2. If I plug in 2 to the -2, right, I'm putting in -2, I get 2 to the power 2, which is 4. Right, so at -2, I get 4. And at -3, I'm sure you can guess, I get 8. Right? Turns into 2 to the power of 3. So like over here, this graph would look something like this. We're going to get close to that x-axis as we move to the right. And so they call this decay because usually when x-axis is time, time moves to the right normally. We're moving forward in time. And so our outputs are decaying or getting smaller. If I were to graph this 4 to the negative x, I'm going to get something kind of similar, right? I'll get, let's say, this point here. It's going to go through that 0, 1 point. They always do. And then at negative 2, that's going to turn into 4 to the positive 2, which is 16. So that's going to go way up here. And then 4 to the negative 3, or negative 3, that's going to become 64. So just to give you an idea, this graph is basically going to start very similar. It's going to be just underneath the blue. And then it's going to shoot up as we move to the left really, really quickly. Okay, so you notice if the base is a bigger number, your graph is going to shoot towards positive infinity much, much faster than if it's a smaller number. We also have our transformation rules that we learned before are going to affect these graphs, right? So, let's say this is my 2 to the x graph, right? So I get something kind of like that, right? That's sort of the basic graph. For transformations, you need to think of the parentheses as being around this little x right here. So remember, what happens on the inside of those parentheses is sort of a left and right kind of transformation. What happens on the outside of them is going to be some kind of vertical transformation. So if I look over here, right, my parentheses are basically around this x minus 3 portion. So that minus 3 is working on the inside of our parentheses. And what that's going to do is it's going to shift our graph 3 units to the right. So instead of going through 0, 1, we go through 3, 1. Instead of going through 1, 2, we go through 4, 2. Right? And so it's going to be a similar type of graph, right? We're going to go through 5, 4 here, over here. It's just going to be shifted to the right by 3. That's it. Really no other difference there. That is a different case as opposed to this one over here, right? So this minus 4 is happening on the outside of my parentheses. This is going to give us a shift down. So instead of going through 0, 1, we're going to go through 0, negative 3. Instead of 1, 2, we're going to go through 1, negative 2. Instead of 2, 4, we're going to go through 2, 0. So something like this, right? And we're going to approach, on the left side, we're going to approach negative 4, kind of like a horizontal asymptote almost. So it's going to flatten out at negative 4. This negative out in front here, right, is outside of our parentheses. This is going to give us a reflection over the x-axis. So we'll get points like this. And so now, right, we're still approaching 0 on the left side, but our graph is going to sort of shoot downward here. Right, so you need to get comfortable with how do we do transformations on these kinds of functions. So it's still the same kind of thing. You take the original graph and you do what the transformation is sort of telling you to do. Are you shifting? Are you reflecting? Right, so we'll fill in these blanks here. So this plus 5 would be a shift left. This minus 5 would be a shift to the right. Plus 3 would be a shift up. Minus 3 would be a shift down. The minus sign in here, right, is going to be a reflection over the y-axis. Right, it's going to flip left and right, whereas the minus sign over here is going to be a reflection over the x-axis. And we also have our stretches and compressions here too for these functions. Like this 1/2 over here would be a vertical compression. by 2. This 5 would be a horizontal compression by 5. The 3 out in front, right, is going to be a vertical stretch. Vertical stretch by 3. And that 1/6 is going to be a horizontal stretch by 6, right? You usually take the reciprocal of any fractions you see. So there you go. Those are the transformations. That's all of them, right? So they still apply, is the whole point of that. The formula for compound interest when it's compounded n times per year. So imagine you went to a bank with a single dollar, and the bank said, okay, you have some options. You can put this money in with us. We'll give you an annual interest rate of 100%, which means they're going to add back to you in interest 100% of your money. All right, so what you would do is you would take this $1 and multiply it by 1 plus 100%, right, which is actually just 1. And it's only going to happen one time at the end of the year, right? So to the power of 1. Well, this is a very simple calculation, right? You're just going to get 2. And if the bank offers you other choices, the answer might change. So they might say, well, hang on. What if we gave you an interest rate of 100%, right, over the year, but we're going to cut it in half. We're going to do half of it in the middle of the year. We're going to apply the interest rate. And so your money is going to grow a little bit there. And then we'll apply the second half at the end of the year. So you take that $1, and this time you're going to do 100% divided by 2, right? Because they're trying to divide the percentage evenly over the course of the year. So you're going to have 1 plus 0.5 to the second power. Well, what is that going to give you? Well, let me bring up my little calculator here. That is going to give you 1 times 1.5 times 1.5, which is $2.25. Right? So you actually get a little bit more money. Right? And, they could keep offering you other options. What if they did this 4 times a year? Right? So you would take that 100%, divide it by 4, right? And they'll apply 25% 4 times in a year. Right? So they'll do 25%, which is 0.25. And they'll do this 4 times, right? That's why we have to the power 4. What is this going to give you? Well, that's going to be 1 times 1.25 times 1.25 times 1.25 times 1.25. That's going to give you 2.44 or $2.44. And so you might be wondering, well, if I keep compounding, right? This is the idea that we're playing with, compounding. When you split the percentage and you apply it more than once in the year. If I do this forever, am I just going to get infinite money, right? If I did something like this, right, 1 over infinity to the infinity, is this going to give me infinitely many dollars? Is that going to work? Well, it actually doesn't, right? There's actually a threshold, a place where you stop making a whole lot of money, and it sort of, it flattens out. Right? Even if you take it and you compound it 1,000 times per year, you actually flatten out at exactly E, right? So this is what E is, right? So instead of getting infinite dollars, you get E dollars, right? So we give it a very fancy name because it's a very important number. It's actually a very important function too, E to the X, right? So you cannot get infinite money. But I do want you guys to know this compounding formula. So if you compound interest n times per year, what you do is you take your principal, we call it P, that's the amount of money you started with, right? So P in this case would be the $1, and you multiply it by 1 plus R over N, where R is your interest rate. So in our case, R was 100%. Or just 1, right? As a decimal answer, it's 1. As a percentage, it's 100. And we raise this to the power n because we're applying this compounded interest n times. So that's the formula. Okay, so that is the interest compounded n times per year. That's the basic formula for it. So that's also going to go over here. But also, if you were to think about what happens if I were to replace this 100% with just the r, right? And if we were to take this as it goes, as n approaches 1,000, or sorry, not 1,000, infinity. Right, so I'll draw a little, this is kind of like a weird form of notation, but basically as n gets bigger and bigger and bigger is what that means. What does this actually turn into? Well, this formula turns into P times E to the RT. Right, and so we call this the continuous compounding formula. This is if you were to basically compound your interest every single moment in time, not just every single second, but every single millisecond or even smaller than that. What kind of formula do you have, basically? You have this exponential formula, right? P times E to the RT. That E is basically your base, right? So this really important number E turns out to be this really nice base for financial calculations. So that's it for the notes.